So my name is Dave Finlay with Couchbase Engineering, and I think we should commence. My machine says 12:59, so I'm kind of waiting till it clicks over to 1, but why don't we get going? Anyway, so today the talk that I was asked to give was a deep dive into Cluster Manager. I wanted to honor that, so we're going to try and go pretty deep today. So let's see where we get to. So first of all, Cluster Manager, it sounds a little dreary. What is it? And well, we first sort of need to begin with a cluster. Cluster, a collection of machines connected via a communication bus of some sort. And what's this gadget you can sort of barely see on the side of the screen? And so this is, this is what I'm bringing this into the talk because I want to try to give you a sense of where we are on our dive into the Cluster Manager. So this is your little depth gauge. And what I'm going to do is leave this on the side of the slides. So as we sort of proceed upon our dive, you will kind of know approximately where you are. We're going to start at the cluster level, move down to the node level, then the OS process actually on a node, and then we're going to go inside Erlang, which is the language that the Cluster Manager is written in, and I'm going to show you sort of underneath the covers and how it kind of works and how it accomplishes perhaps the most important sort of collaborative piece that we do in Couchbase Server, which is a rebalance, how that actually works. Okay, so this is going to, as I say, will sit on the side. It'll give you a kind of visual indicator of where we're at. So anyway, the nodes in the cluster, you install Couchbase on them, and they start talking to one another. And the nodes themselves are combined with a number of OS processes that collaborate and talk to one another. And part of that, two of those processes, in fact, are really what is the Cluster Manager. So that is the Cluster Manager. In some sense, it's the brains of the organization. If sort of memcached are the legs, then Cluster Manager is the brains of the operation. So, what does the Cluster Manager do? Well, it does lots of stuff. And these are, basically, it sort of coordinates everything. So it manages the services on each of the nodes. It manages the data topology and the associated replications, because obviously in a shared nothing architecture, it sounds very cool, but it kind of means you have to copy a lot of data, that you spend a lot of time copying data. Provides metadata services, authentication and security-related stuff, a REST API for people to administer the cluster with, UI, and then it gathers all sorts of stats. And if anything's ever gone wrong with your cluster and you've had to look at the statistics, there are tons of, we gather tons of stats about everything. And then simple alerting to let people know when things kind of have gone wrong. Okay, now what I'm going to do is show you, we've dropped down a level on our depth gauge. You can see the little green dot has moved down one level. Now we're on a node. And these two processes, and if you remember one thing, when I did a dry run of this talk some time ago, and the thing that came through was people didn't remember this bit. So if you remember one bit, remember that the processes in red constitute the Cluster Manager, the two processes that work together. So there's a babysitter process and the NS server process. But there's this whole array of other things going on, and let's kind of take a quick look at those. So remember, the red processes are the Cluster Manager. So memcached, this is the first of the other processes that run on the node. This is actually kind of, in some sense, an optional process. As part, you might have heard a little bit about our multidimensional scaling. So you can, memcached is sort of quote unquote deployed on a node if that node is a data service node, and obviously it manages KV requests. And now there's a number of other processes that are also associated with data service. So XDCR, View Engine, and there's others besides smaller processes that do smaller things. And these are also co-deployed on a data service node. And actually, this is kind of interesting. So XDCR and View Engine, this is a change from 3.0. So one of the things we wanted to do was was actually carve these relatively data-intensive services out of NS Server. Previously, they were part of NS Server. Carve them out and make them their own independent OS processes. So they don't, if they go wonky, they have less chance to cause collateral damage, to the brains. So that's a change from 3.0. And then there's Indexer, which kind of, as the name implies, does indexing and then allows people to scan indexes. And John gave a deep talk on how that works and how the data is managed to it yesterday. This is also an optional process, so you can be data and or indexing on a given node. And lastly, we have query. So query is deployed on query nodes and serves nickel requests. So the babysitter, its job is actually relatively simple. It starts, manages, monitors, and restarts these nodes. So, oh no, it's the chaos monkey. So there was a chaos shark, but I guess this is a tip of the hat to Netflix. The chaos monkey comes along, kills one of your processes, and babysitter will take care of it, and the chaos monkey is disgruntled. So babysitter has a relatively simple existence. Its job is simply to manage the tree of cooperating processes on the node. So NS Server, the other part of the babysitter, let's talk about that. Now, it's written in Erlang. And here's a kind of relatively dull architecture diagram showing the different kinds of services which are inside NS Server. So we have like generic local facilities for managing local configuration and sort of libraries and other sort of useful constructs like work queues and vector clocks and that kind of thing, logging management. Generic distributed facilities, so obviously, we're interested in the node itself, but only to some sense, to the extent that it cooperates with the other nodes in the distributed cluster to accomplish stuff. Per node services, monitoring, that kind of thing, per bucket, basically. So obviously, bucket is a key concept for us. It's where your data is. So we carefully manage those buckets and make sure they're healthy and fail them over and things like that. And so that's in the per bucket category. And then a REST UI, and then a REST API and an associated user interface. So you both have kind of an easy sort of user-friendly way to interact with the system, but also you can script it and stuff like that. Master-only services. So in an ensemble of nodes, it's very typical. In fact, it's kind of the way one accomplishes many things is to elect a leader of that cluster, to elect a master. And then most of the cluster-wide activities are then coordinated through that master. The master needs to be highly available, so if it dies, another node needs to take its place. And so that's part of the facility we have. And that's in the little red box, the master-only services box there. Okay, so to get more detailed, because as you see on the depth gauge, we're now kind of at level 3. We're inside a process, but we're going to go down now even one level further to the Erlang processes. We need to in order to sort of communicate it effectively, I need to teach you a little about Erlang. So if you know this stuff already, this is review, and if not, maybe you'll enjoy seeing a little bit about this kind of interesting language. So a little bit about Erlang. So it was developed in the 80s by Ericsson, a Swedish telecommunications company that many probably have heard of, for use in phone switches. And this famous switch, the AXD 301, there are some ridiculous claims about its reliability. 9 nines I've seen in things on the internet, which doesn't mean much, I guess. But anyway, if it really was that reliable, that amounts to about 1 second of downtime in 30 years. But even allowing for the hyperbole, it was pretty reliable, right? And these are telephone switches. These are not things that you want to really log into and reboot. These things need to just work. What's cool about it? Well, this is taken from a paper. There's a bunch of stuff that's cool. I guess I would highlight it's really designed for concurrency. It's designed for distributed systems. It's a high-level language that lets you do a lot with a very little bit of code. But let's get a little more specific. So I want to highlight two things that I think that make Erlang cool and useful for what we do, and also may even change how you think about creating software. Now, the first thing is that Erlang is an actor model style. It's functional, which almost implies, maybe not quite, implies that an actor model style of programming. So, there's a core concept at the core of the system, which is this idea of a lightweight process. It's not a thread. It's much lighter than that. But it's an entity that's responsible for, so it has its own lifetime, and it can do stuff. And then it has a mailbox, an inbox queue, right? So messages can be sent to it. So if I've got two processes, process P and process Q, I can send a message from one to the other, as simply as shown in the top right-hand corner. And so these values are immutable. In fact, Erlang is a single assignment language, so variables can only achieve a value one time, and then they can never change, which twists your brain when you think about it for a little bit. So there's no way to accidentally share state or communicate across processes. The only way to do it is to send a message. And then you can receive those messages and reply to them. It's very simple. And you can receive what's called selectively. You don't necessarily have to take the first thing in the queue. There's a description of how that works. And I guess one of the things that this sort of manifests as, or one of the sort of things that occurs as a result of this is, it's kind of hard to get deadlocked. It's asynchronous by default, and you have selective receives. It's kind of hard to get deadlocked, but it's possible. Now these things that I just showed you, these can happen within a given Erlang VM, or across two Erlang VMs, and those things could be on the same node or on a remote node. And from the programming perspective, the feel is exactly the same. There's no difference. You just find the object by name, or find the name of the object that you want to send a message to, and you send it. And everything else gets taken care of for you. So it's very powerful, it's very seductive, but in terms of coordinating activity across a distributed system, it's kind of delightful, because otherwise you will spend your time writing this in C yourself anyway. And so, as I say, the behavior of this message passing behavior is the same in both cases. The second thing I want to highlight is OTP. So OTP stands for the Open Telecommunications Platform, or Open Telecom Platform, and that's fine. But what it really is a framework that provides useful higher-level constructs built from the Erlang primitives. So such as this gen server. So gen server is probably the most fundamental thing you have in OTP. Generic, stateful, startable, stoppable server. So you can certainly write it yourself. In fact, it's probably a good idea to do so once, just like it is you should write a linked list and a hash table once. But then you want to take advantage of this construct. And when you come to program, you'll think about it. Oh, I need a gen server here. And you just essentially invoke the framework, provide the appropriate callbacks, and you have your entity that you can now deploy in your system. The second thing I want to point out about OTP is this notion of supervision. So basically, supervisors, you declare them. They're responsible for things, other processes, which may, of course, be supervisors themselves. So it's immediately a recursive or at least inductive structure. And it's responsible for starting, stopping, monitoring, and so on. And this is declared. You have different kinds of behaviors. But if our chaos monkey shows up again and takes out a gen server, well, no fear. Supervisor will be started, and if the system can get back to normal. And this, so this kind of notion of self-similarity between what happens at the OS level with Babysitter and what happens within the Erlang process via the supervisor framework. And in some sense, the idea of restarting things is a very simple idea, but it's kind of core, it's a very effective fault tolerance construct, and it's used heavily, not just by us, but by lots of folks. And so Erlang has really captured that in a nice way. Okay, so now we're going to, so that you've kind of took a little detour into Erlang. I want to come back now to NS Server. So if you remember, we left off in NS Server. I showed you this kind of large block diagram of how it was all structured. I'm going to come back now. So inside NS Server, so there's a thing called the application. An application is another OTP construct and really just describes the bundle of code in your app. And its job is essentially to instantiate the top-level supervisor. So this is the supervisor of the supervisors, or the capo dei tutti capi, if you like a mafia reference. And so its job is kind of to be the culmination of all of the supervision, all the processes all the way up to the top. Okay, so it supervises the supervisors. And as we drill down, it's got some interesting child processes attached to it. The config supervisor, which is responsible for managing, storing, updating, changing config notifications. What we're really interested in today is the server node supervisor, which is sort of the most important secondary supervisor that's going to influence the talk today. It's the main one. And the NS cluster gen server, which performs node join leave requests. And there's some other stuff that's pretty interesting, but we're not going to talk about it today. So as we move down the hierarchy, now we're in the NS server supervisor. And there's some interesting parts of this. So the master process is a gen FSM. It's a finite state machine, which is another construct out of OTP. And it's responsible for master election. So it's the process which coordinates with the other processes and the other nodes in the cluster to elect a master, and then fail that, should that master cease heart beating, elect a new one. The node that is the node that elects the master, its job then is to create singleton processes for the whole cluster, such as the orchestrator, which then a lot of the cluster-wide activities get channeled through. The node discovery supervisor is a key bit. As nodes go up and down, you get notifications about these things. Those notifications get routed through the system so people can take actions on the basis of it. The Menelaus supervisor is responsible for the REST API. The Greek name, so Menelaus, won out over Ajax in terms of winning the hand of Helen of Troy. So sort of Menelaus is the boss of Ajax. We wanted a nice Ajax-y back end for our, that's the origin of that. And here, so now you're probably getting a little dazed with all these things flying around. But here we have the bucket supervisor. So as we proceeded down the supervision hierarchy, and so this is responsible in some sense for managing your data on that node. As you come down, you'll see we have a memcached supervisor, and its job is essentially to communicate with memcached, to make invocations against it, to gather stats from it, and connect that all up into the system so that we can monitor and track it. The replication manager and the DCP supervisor. So every node is responsible for its inbound replications to it. So we have, obviously, many of you will be familiar. We've sharded our buckets into vbuckets, typically 1024 vbuckets. We distribute them around the cluster, and we distribute replicas of those around the cluster in a way that is maximally balanced. And so it's not only balanced in terms of workload, it's balanced also in the event that we have a single failure. So the system is still balanced, so you don't have this cascading race to the cliff. So each node knows about the replica buckets that it needs to stream. And so we have a sort of a pull model. So as a node, I know I need to go to this other node, and I need to pick up like 5 buckets from him and open DCP streams against those. So that's the job of that supervisor, to do that. And the replicator, there's one replicator per replication stream. Right? Okay, and then lastly, there's the janitor agent. The janitor is responsible for keeping things clean and tidy. And also, we leverage it heavily as a sort of a remote communication facade. So when I'm talking to a bucket, essentially on a different node, that we mediate the communication typically through the janitor agent just by sort of convention. Okay. All right, so pause, take a breath. We're at the bottom. We're deep in Erlang now. We've seen a little bit about Erlang and how it's used and why we think it's useful for this kind of problem. We've taken a look through the supervision hierarchy. Now what I want to do is I want to take you through how these processes collaborate, these Erlang processes collaborate to do replication, or to do, rebalance, which is, it's a little button on the UI, but it's kind of like launching a fleet of battleships. in some sense, it's just a lot of activity happens. And the goal, of course, is that we're going 90 miles an hour. There are, I don't know, there are 200K operations a second coming in at your cluster, or 1 million. And you want to rebalance, and there should be negligible impact to the system. So you're going 90 miles an hour, and you want to corner, a 45-degree corner. You can do it. You just need to make sure you bank appropriately so that you're going very fast. So you need to take care that everything is just done right. So let's talk through that, how this works. And so this is sort of the NS server in action. So it all starts. The user clicks a button, a rebalance button on the UI, or they send a REST API request. It goes to a particular node. That node looks up the orchestrator and says, hey, can you rebalance? The orchestrator, it's in the idle state, and it says, sure, I'm idle, I can do that. It changes its state to rebalancing, and at the same time, it conjures up a new rebalancer process to take care of it. And of course, if it were already rebalancing, because it's a single point of, a single route, a single gate, it would reject it and say, I'm rebalancing. You can't initiate a rebalance while a rebalance is happening. So now let's look at the rebalancer. This is the process that's conned up to take care of it. So what it does is it's going to iterate through we rebalance bucket-wise. And in some sense, we want to be cognizant of the time, but we're not in a hurry to do it really quickly. Rebalance obviously does, as I talked about, a shared nothing architecture, so there's a lot of data copying that needs to happen. You might have tens of gigabytes on a given node, right, very commonly. And you're going to need to move some proportion of that. Typically, if we do our math right, you're going to move about 1 over n of that data to other nodes, where n is the size of your cluster. So if you have a cluster of size 20, you add a 21st node, you're going to move about a 20th of the data. There's no other way to do it if you want to keep the system sort of maximally balanced. So we're going to iterate bucket-wise. So we'll do it sort of serially. And then the bucket mover will generate a new vbucket map for itself. And it will sort of compute the diff, like this is where I'm going to, this is where I am, what are all the things I need to move? And it will do it in such a way that each node is only involved with moving buckets sort of at one point in time. So in other words, we won't schedule all of the moves to happen on a single node, inbound or outbound. So we kind of make sure that we sort of balance the work. And what we do is we look at it and we say, okay, well, we need to move this vbucket from A to B, and we move this other vbucket from C to D. So we're going to do these concurrently. So I'm going to create single vbucket movers to do this. And then when those single vbucket movers are done, they send back to the bucket mover. It runs through all the buckets, finishes, rebalancer is done. But that's not the cool part. So let's get to one level deeper. Now let's look at the single vbucket mover. Like, how does it actually do it? How does it actually move a single vbucket while furious gets and sets are happening at the same time? So in this slide, we've got, if you recall, the initial request came in on the master node from the remote, from the UI, got routed to the master node from whatever node received the request. And of course, there are now two different nodes that are involved in the vbucket moving. Now, I'm only going to focus on moving I'm not going to focus on moving the replica vbucket. I'm just going to focus on moving the active vbucket. And the active vbucket is in the from node, and it's the little green rectangular type thing in the bottom right-hand corner. So we start by this. We send a note to the janitor agent on the two nodes saying, hey, you need to sort of pick up a new replica of this guy. And it will contact the DCP supervisor and say, can you create a new replicator for me and start moving this stuff? And we'll start streaming that data through, right? The next thing we do is the single vbucket mover goes to the janitor agent on the from node and says, hey, can you tell me when you're almost done? Can you just keep pinging the replication queue in that memcache stream and see when you're almost done? Let me know. So now it's down to a trickle. Essentially, the backfill is done. Now we're just kind of catching up with the current activity in the system. So we go back to the vbucket mover and tell him, we're done. We're ready for the final coordination. Now at this point, of course, on the from node, that's still the master node for that vbucket. So all of the requests are still coming in there. however many that is a second. And they're getting replicated, immediately or very, very, basically in real time to the new replicate we've created on the 2 nodes. So the from node is still the active copy. And now we use a primitive out of DCP to affect the final handover. So this is what happens. So we send a takeover message. I'll go through it again. But basically, we send a takeover message to the new node saying, hey, can you shut down that stream and open a takeover stream? And the job of the takeover stream is just as it describes. It will instruct memcached in the from node to stream that stuff. And when it gets to a point that the queue is empty, it will shut it down, declare that it's not the owner of that vbucket anymore, and on the DCP stream will instruct the remote client, you should start advertising yourself as the active copy of this. So that's what happens. Let me just play it again. You'll see it. We send a takeover request. It goes to the replicator. In some sense, we kind of convert the stream to a takeover stream. Then this replica becomes dead. The new replica on the 2 node becomes active, and replication is complete. Okay, so I guess we're all the way down, and I guess maybe the one interesting point is that obviously, you look at the simplicity of the action, on the UI, but underneath the covers, there's a lot of activity, and a lot of monitoring, a lot of checking, and to make this all happen so that we can continue to serve requests, with the tiniest blip when we flip over from one active vbucket to another. I'm going to bring you back up just to remind you, so not too quickly, so you don't get the bends from our dive. This is inside NS server. This is the sort of subsystem diagram. NS server is in this node, which is part of a node deployment on part of one of the processes deployed on the node, and here's our cluster. So that brings us all the way back up to the top. And that's it from me. So we have time for questions. I see. Have a question? Yeah.
Yeah. Could you clarify the relationship between the web UI post that the administrator logs on and the master node in your slide?
Okay. So the question was, if I don't get it right, just let me know. So can you clarify the relationship between the node that receives the request to do the rebalance and the master node? So. So we have a very homogeneous cluster. So all nodes kind of look the same. And when you log into the UI, you'll pick one of the nodes to log into. And that's random. You'll just pick whatever one. And then when you click rebalance, the node that you logged into will be the first node to receive the request. And then what it will do is it will look up, well, it doesn't even have to look it up. It just says, I need to send this message to the rebalancing message to the orchestrator. I have no idea where that is. All I know is that its name is global orchestrator. And it sends a message to the orchestrator saying, please initiate a rebalance if you can. If it can, it will change its state and send a message back to that Erlang process saying, we are rebalancing now. You should please report that to the client. And if it can't, it will do likewise. So that the node that receives the request is sometimes random. It's just the node that you decided to pick to log into or to issue the REST API request against. And the master node is elected from, you won't know which one it is typically. But does that make sense, or is it a bit confusing?
Well, you mentioned this message to the orchestrator is from the node that receives the request.
Right.
In the slide, it's sent from the master node.
Well, let's go back. Let's see if I can do that. So the node that receives the request is any node. Oops, so it receives the request and then sends the message to the orchestrator on the master. So those are not they may be the same, but they're not necessarily the same. Yep.
So, this might be a slightly different topic, but your overall architecture is based on peer-to-peer. Now, why this is a massive, couldn't you use a similar strategy so that you don't have a single master and then have
So the question is, our architecture is based on a peer-to-peer architecture. Couldn't we do the same with a distributed algorithm that we don't necessarily need a single point to route it through? Possibly. Just in sort of my experience with distributed systems, it's very common to elect a leader to coordinate single activities. And then the main thing is to make that leader highly available. There are systems, of course, like the internet, which is a good example, where electing a leader is simply not possible. The network topology is too dynamic, it's too large. There's no way to identify a single node on the system, that can do things. And so we typically use, different algorithms in those kinds of cases, like the way routing is achieved. So we have hierarchies, and everybody has a partial information. Nobody has all the information. On systems of the size that we're talking about here, and of those of our competitors in the tens or hundreds, or even maybe low thousands of nodes, something we don't scale to today, but having a single coordinator works really well. So it's simple, simple, and it works. And even if you look at things like Raft or Paxos or Zookeeper, consensus protocols leverage the idea of having a single master to coordinate activities. It's just fast, and it's much less. It's much less like you already are in the realm of having potentially subtle conflicts and things that are difficult to reason about. Having a single master makes it simpler, and it works very well. So, I think there was a question here. Yeah.
Two questions,
Yeah.
kind of related, I think. If we add like multiple nodes and want to rebalance everything together, is that possible?
Yeah.
And there is a failover that is happening. Does it have any effect on the rebalance?
Good question. So first question was, if I add two nodes and I rebalance, does that work? Absolutely. So basically, you add as many nodes as you want to rebalance and hit the rebalance button. We'll compute the new vbucket map, diff it, and then apply the logic that we just walked through here. Auto failover, does it cause a problem? So I think if there has been an auto failover, you need to acknowledge that failover, I think, before a rebalance can be initiated. So in a failover situation, what happens is either a human or we decide, if it's configured that way, that this node is no longer serving requests. And we don't actually rebalance. We just immediately allow people start accessing the replicas, right? So you want to acknowledge that node is down and take it out, and then you initiate a rebalance at that time. So you can continue serving requests quickly. You just immediately appoint a new master copy of each vbucket, and then so the system was working, but now you're short a copy. So you need to rebalance at that time. It's going to identify nodes on which we need to create replicas so that we have the configured number of copies of each of the vbuckets. Oh my goodness. How about here?
So how do you do orchestration automation, and how do you determine the best granularity of your microservices? You have so many microservices. And the last question is, so far, what is the biggest challenge in your cluster management?
Okay.
How do you
Good question.
deal with that?
Okay. So the first question was, how do you? I missed the. Can you repeat the first part?
Orchestration automation, because I missed
Yeah.
your
Oh, okay. So we can talk a little offline, but basically we elect a master. That master is responsible for creating the orchestrator, and then all of the cluster-wide activities are routed through that single source. On the second question, what's the biggest challenge we have in terms of the cluster manager? Of microservices. The microservices, not too fine-grained, but pretty fine-grained. So certainly having microservices responsible for a bucket or a replication is fine and very appropriate. Having microservices responsible for serving an admin request, not really. So you don't want to get too. You need to choose the right level of granularity for things that they're not very heavyweight, but you shouldn't go crazy and have tens of millions of these things. Thousands, even hundreds of thousands is fine, but not tens of millions probably.
So your orchestration automation is 100% automatic? 100% automatic?
Is it 100% automatic? I'm tempted to say yes. I'm also tempted to say no. Well, so we do have auto. Yeah.
Service discovery?
Yes. Yeah. So the biggest question, the biggest challenge we have right now, I'm not quite sure what to pick.
So you solve all of them?
No, definitely not. We definitely haven't solved all the problems. I think our failover time, I'd like to reduce that. That's a significant challenge. Yep.
What protocols are you using to replicate the data from one node to another, and how do you ensure the data integrity across the nodes?
DCP.
Okay.
That's how do we? I mean, DCP is a core Memcached, part of Memcached. It's a protocol that we wrote some time ago in 3.0 to essentially to be a sort of a next generation data replication protocol. And obviously we rely on, and at the cluster management level, we rely on DCP being correct to ensure that that we have data integrity across the system.
Do you get some sort of feedback that says, the data's good? Or
Well, we get feedback that the DCP stream is done, and
you don't get any feedback saying that the data's integrity?
in some sense that's the responsibility of Memcached to ensure that to us. Yes, one more question here. Yeah.
So I have a question about the logs.
Yeah.
Not really readable.
Okay.
And I think we have complained enough about that. So I'm wondering what your thoughts are. What do we do with, we have a number of 2.5
Yep.
clusters, and even in 2.5, logs are not that readable. So when we need quick turnarounds on what's happening to a cluster, and we need to make a decision based on those logs, I'm just wondering, how do we do a better job of being able to read those logs?
It's a good question and a fair question. The Erlang logs can tend to be a little inscrutable. Of course, they're sometimes a little bit difficult to read because the way Erlang formats the output is a little unfriendly, maybe. But of course, I think the other part of it is that there are lots of activities happening that, even with a sort of a kind of a Java style, log4j kind of output, you'd still struggle a little. I mean, one would still struggle a little bit because, as you talk through rebalance, you can see there's a lot of coordinated activities going. I'm initiating a DCP stream here. I'm setting a takeover stream here, and it's hard to see the big picture of where we are in the process when something got hung. It's almost like you need to look at all the logs in some sense to get a sense of how far through the rebalance you got before things went boom. And so I think there are probably at least two problems. First problem is Erlang's a little unfriendly. Second problem is the orchestration and logging associated with that. The orchestration is not simple, and the logging associated with that is difficult to reverse engineer and get this picture of create this picture of where you are. The one thing I would say in defense of the logs is that the cluster manager, because it's not dealing with a lot of data, I mean, it's dealing with quite a bit of data, certainly in terms of DCP replication, but in general, most of the activities are not, they're admin activities and they're management activities, and so we log pretty heavily. So the one thing I'd say is that when we get the logs, when Couchbase receives the logs, there's lots of information for the guys who know how the orchestration works to actually debug it. And I understand that's definitely a step down from customers being able to self-debug, and I acknowledge your point that we need to do a better job there. I want to take one question from way in the back. That question, yeah. That's a very good question. I believe we copy we don't just rebuild the replicas, we copy them. That's my understanding. I should know the answer to this straight cold, but I believe that's the case. Oh, well, what does a bad replica mean? To re. Yeah. I don't have a good answer for that.
Will it actually initiate a rebalance if it detects that there's a inconsistent data or invalid data or something?
No.
You don't want to do that.
No.
There should be some sort of security.
No, yeah, exactly. So just to answer your question, let me think about that. We can catch up afterwards. I don't have a good answer off the top of my head. I haven't, in my time, I haven't seen such a case, but you may well be asking from real experience. So I don't know. Yeah, so a rebalance, basically, we don't auto kick off rebalance ever. That's an activity which admins will invoke on the system in some form. I'm going to finish up. Thank you very much, and get ready for the next presentation.